Good afternoon, ladies and gentlemen, and welcome to Chapter 6, where we're going to be doing momentum and collisions. I have here the handout that I've uploaded for you, which is the chapter summary of Chapter 6. And so the first two sections is momentum and impulse, and then conservation and momentum. So we're going to work on the practice preparation problems for practice A and practice B in this video. All right, so the big deal, momentum, very simple calculation, just mass times velocity. That's it. You already learned kinetic energy, which is mass velocity squared divided by 2. So you're just mass times velocity. And then we're going to talk about what impulse is, which is the change in momentum. So we have delta P. We use lowercase p for momentum. Delta P is the change in momentum. So that would be mass times velocity final, that's your final momentum, minus mass times initial velocity. Then it turns out that the change momentum is also the force times the time. So that's in practice C homework. And so force times the change in time is your change momentum. So force times delta T is mv final minus mv initial. All right, so let's get to the problems of practice A. This time I finally got smart and made a copy of the page from the heavy book. Okay, so let's see. We're on page 223, chapter 6, the problems for practice A. So here we go, number 11. Hopefully you can see this. I'll make it bigger. So they give us, says the proton has a mass, calculate the linear momentum. Calculate the linear momentum for each of the following cases, A, B, C, D. What is a linear momentum? Well, we know momentum is lowercase p, which is equal to mass times velocity. That's what momentum is. All right, so they gave us the proton with mass 1.67 times 10 to the negative 27 kilograms. It's moving with the velocity of 5.0 times 10 to the 6 meters per second. So the only thing you really need to know about these problems is the units for momentum needs to be kilograms. Our mass is kilograms times, and velocity must be meters per second. So that's what the units should be for momentum. All right, where you know that Newton, by the way, is kilograms times meter per second squared. That's a Newton. But for momentum, it's just kilograms meter per second. So we always want to look and make sure what our units are. They gave us mass in kilograms, meters per second. Cool. So we just multiply those two. In B, they gave us grams. Grams and meters per second. Well, that's not okay. So we'll need to convert the grams to be kilograms. Just like in your lab, you were supposed to, for kinetic energy, take the mass of that rubber ball, which I gave to you in grams, and you have to convert it to kilograms. All right, the next one, we've got kilograms and we've got meters per second. Now notice they tell you southwest. Do we care? Yes, we do, because we know that velocity is a vector and velocity has a direction. So therefore momentum is also a vector. Mass is just scalar. So scalar times vector is going to be a vector. Okay, so here they told us it was straight up. And the next one they say to the right. And the next one they say southwest. All right, let's see. The last one, really big mass, 5.98 times 10 to the 24th kilograms to a velocity, pretty big velocity, 29,800 meters per second. So what you're going to find in this chapter is everything is really straightforward. You're just going to find out if you really know how to use your calculator, because we're going to be sometimes dealing with really big numbers. And in the following, get to gravitational, we have really, really big numbers. So the computations are easy, but you need to know how to use your calculator. All right, so let's do this, make sure we know how to do this. Let's start with the first one. I've got the mass is equal to 1.67 is a proton times 10 to the negative 27 kilograms. And I got my velocity here is 5.00 times 10 to the 6 meters per second. And they want to know what the momentum is. Well, momentum is just mass times velocity. So I'm just going to multiply those two. So for those of you who need a review on how to use the calculator, let me make this smaller, I guess. You can see what I'm going to do here. All right, hopefully you can see what I'm with the calculator. I guess I have to stand up here, maybe. I can't see. All right, so the first one, 1.67, and I'm going to say times 10. I just got to do 10, and I'll use the caret. There's that little caret right there. And I'm going to say negative 27. Now, to be able to multiply something else, notice how the cursor's up at the exponent. I have to hit this button to bring it back down. Okay, times 5 times 10, and again to the caret, 6. Now I just hit enter. See the answer, and there's my answer. 8.35 times 10 to the negative 21. All right, so remember, you always have to include units, otherwise you don't get full credit. 8.35 times 10 to the negative 21, and your units would just be kilogram meters per second. Okay, so there's our first one. There's our first one. Let's do our second one. Oh, and it did say straight up, by the way, so we'd have to go up or straight up or some sort of direction because it is a vector. All right. Too bad I didn't move over more to the page. Okay, the next one, I've got a mass of 15 grams, and I go, wait a minute, I need kilograms, so I'm doing momentum. So let's change that, divide that. If you don't know, I've got 1,000 grams to 1 kilogram. Okay, so that means I move the decimal place over 3 times. So I got 0.15 kilograms. Okay, 0.15 kilograms, and then my velocity is 325 meters per second to the right. So I'm just going to multiply those two. Clear. 0.015 times 325. There we go. So I end up with 4.875 kilograms meters per second. All right, let's take the next one. I think you're realizing this is pretty straightforward. Come right here, C. I got 75 kilograms, and I have a velocity of, oops, this is the mass. Velocity is 10 meters per second south to the southwest. All right, so what's my momentum? My momentum is just the mass times the velocity. So I have 75 times 10, 750 kilograms meters per second to the southwest. That's good. All right, lastly, I just want to show you guys how to use your calculator for those of you who still aren't comfortable, or confident, I should say, confident in the use of the calculator. Here we go. We have a big mass, 5.98 times 10 to the 24th kilogram. Our Earth is heavy, and it moves at a velocity of 2.98 times 10 to the 4th meters per second forward. What is forward? Well, I don't even have to say it goes around the orbit. Forward. Forward's good. Okay, so the momentum is just mv. Let's see how we use our calculator for that. I've got, let's see if you guys can see here, 5.98 times 10 to, they use the caret, and this is a big one, 24. Again, I have to hit this button here to make it come down, times 2.98 times 10 to the caret 4, and I get a big number. I get 1.78 times 10 to the 29th kilogram meters per second. All right, so this was super short. We're going to go ahead and do the one for practice B. Let's look at the problem for practice B. All right, see if you can see that. Number 12. I'll make it big so we can see number 12. All right, here we go. We have a ball, 2.5 kilogram ball, and it strikes a wall with a velocity of 8.5 meters per second to the left. Okay, so we're going to have to use signs to show direction. The ball bounces off with a velocity of 7.5 meters per second to the right. If the ball is in contact with the wall for 0.25 seconds, so a quarter of a second, what's the constant force exerted on the ball by the wall? All right, so as I showed you on our summary sheet for page 6, we have something called the impulse, the change of momentum. And that results in external force applied in a certain amount of time. All right, so there's the force times the time is equal to the change in momentum. So that's the one we're going to want here. So let's rewrite the problem. Okay, I'll flip the book over. There we go. Okay, so up the top. So what do I have here? Always rewrite or translate the problem. First, we have a mass of 2.5 kilograms. So we have a wall and a ball goes, oh, you can't see my picture. A ball goes smashing to the wall and it tells us what the velocity is to the left. So the first velocity, we're going to call it V initial or V1. V initial is negative 8.5 meters per second. After it hits the wall, it smashes to the, goes towards the right. I'm just going to draw it this way. Seems to slow down actually, and it slows down. Now it's going 7.5 meters per second. So the magnitude is smaller and it also changed direction. All right, so it goes to the left, a left 8.5 meters per second. And we want to know what is the constant force. And we know that it took about quarter of a second was the time that was in here. So in here, it's about quarter of a second. So we want to know what the force is. What is the force there? All right, I got this too big. Let me unzoom now. Okay, so we've got the mass is 0.25. And then the initial, I'm going to write here, initial is 8.5 to the left. So I'm going to say negative 8.5 meters per second. And then my final is positive 7.5 meters per second. And then we know that it's the time frame. There we go. The time frame, the delta t, is a quarter of a second. Quarter of a second. So we want to know what's the force. What is the force? Okay, so what's the force? So I know that the change in momentum is the force times the time. So if we want to know what the force is, well, all we have to do is divide the time, both sides, right? Divide the time to both sides. But first of all, what is the change momentum? Okay, the change momentum is my mv final minus mv initial. Because remember that the momentum is just the mass times the velocity. So if I've got my final momentum, here, let me write this. The change of momentum is my momentum final minus my momentum initial. Notice it's a lowercase p. Momentum final minus momentum initial. So there we go. mv final minus mv initial is equal to F delta T. And we're interested in solving for the force. Now, you guys notice I'm going to be taking points off if you don't solve for the variable. This is going to get kind of hairy quickly. It's very simple and straightforward, but it's going to be a lot of numbers. So it's really, really efficient and faster to just solve for the variable that you want. But before I do that, I noticed the mass didn't change. So why don't I factor out a mass? Now I don't have to, but it's going to mean less writing, less computation. So if I factor out the mass, I end up with the mass times V final minus V initial, and that's equal to the force times the time. So I'm interested in the force, so why don't I divide both sides by delta T? So now my delta T's cancel out, and I end up with the force is equal to mass times V final minus V initial all over delta T. Okay, now I can plug that in. So let's see, what do I have for the mass? I have 2.5 kilograms. Now here's where I really want to make sure I'm careful with my signs. My V final was positive 7.5. So I'm going to say 7.5 minus my V initial is negative, minus a negative 8.5. And that business is meters per second. All that divided by the time. and the time is 0.25 seconds. All right, so what's 7.5 minus a minus? What's 7.5 minus a minus 8.5? Some of you guys know I don't like to subtract, I like to add. And when you add, subtraction is the same thing as addition, but you got to change the sign of the other one. So I just go, so it'd be like 7.5 plus 8.5. All right, so yeah, you can do it on your calculator, but you should already understand this. So I end up with 7.5 plus 8.5. Okay, I like avoiding my calculator. So 8 plus 8 is 16. So I have 16 there. So I have 2.5 kilograms times 16 meters per second. I should write it underneath there, divided by seconds, 0.25. And that's my force. Now notice that I have meters per second, seconds. I end up with, this is kilograms. So I end up with kilograms meters per second squared. Good, because that is a Newton. So I know I did this right. I know I got the units right. Okay, so now let's multiply all this. And we get 2.5 times 15 divided by 0.25. And I end up with 150. Is that right? What did I do wrong here? Did I not put something together? Oh, sorry, this is supposed to be 16. This was supposed to be 16. Right here, 16. There we go. Let's try it again. 2.5 times 16 divided by 0.25. There we go, 160. That's why I check. 160 newtons. So I get that the force is 160 newtons. Now, a force is a vector, so I have to give it a direction. And so I ended up here with the positive direction, so it would be to the right, because it's positive. So to the right or positive, either one. Okay, so let's see what we did here. Okay, most important part is, this is the problem where you're actually learning to use that there's a correlation between momentum and force and time. So we have the change in momentum is the force times the time, but the change in momentum is just the final momentum minus the initial momentum. So you don't have to, but you'll notice it ends up being a lot cleaner, less computations if we just factored out an m. Factored out an m, so I have F delta t is m times the change in velocity, v final minus v initial, all over t. So to isolate the F, just the F, then I divided delta t to both sides, and I end up with the force is the mass times Vf minus Vi all over delta t. Plug those in, and if you doubted me, I'm going to do this 7.5 minus a negative 8.5, and it was 16. So that's what should have been here. 16, and then times my mass, which is 2.5, and then divided by the time, I ended up with 160 newtons. And that's it for the problem for practice B, and I'll see you next time.